Hello, everyone. Welcome to another episode of Isolation Intelligence for Odell Associates. We appreciate you joining us today. I am just going to, this is Nathan Martin from Odell. I am just going to give about 2 or 3 more minutes here, maybe 2 minutes, to let all the attendees who have signed up get online, and then we'll get started. So just another couple minutes, and we'll be started. Okay, looks like we're getting pretty settled out there on the attendees. So I will get us started on this episode of Isolation Intelligence, where we're going to be talking about Valent, DOAS, Dedicated Outdoor Air System Solutions, and drilling down into some efficiency, refrigeration, and codes. So just a couple introductions as to who's going to do the presentation today. Both myself, I'm Nathan Martin from Odell Associates, and Brian Jennison, who's the area sales manager for Innovent, will be taking on the presentation today, and we'll be going back and forth to provide you with some information as we go through the day. Brian, is there anything you wanted to say?
I think you said it pretty well, but thank you for your time today. We know it's valuable and we appreciate you being here with us.
Yes, sir. One last thing before I move on to the actual presentation, a little bit of housekeeping that I forgot to talk about is we're in listen only mode at the time being, so you're going to only be hearing from myself and Brian. There is the opportunity to ask questions on the side there to your right. Little question bubble. If you want to ask a question, by all means, type a question in there, and we will get to those at the end of the presentation. If you need something or would like something answered immediately, just also put up your hand. And we also have Cam standing by, and he'll interject and interrupt us so we can get any questions answered that are looking for an immediate response.
Hello.
The other thing is this presentation, along with all the other 17 webinars we've done through isolation, are all available on our website. Both the PowerPoint slides as well as the video of the webinar are available on our website under the resources tab. You can go through those and check through anything that you'd like to look at. So moving on to the presentation. So this presentation, we're going to first talk about dedicated outdoor systems and define those and the challenges presented with that style of equipment. We'll talk about the Valent product specifically with just a brief overview of what we offer. Then we'll get into the DOAS design considerations with respect to capacity control, dehumidification, and efficiency. And I'll finalize that with some discussion on DX cooling specifically and efficiency codes in Ontario. So I will let Brian take it away from here.
Great, thanks, Nathan. So before we dive too deep, I want to start out with a definition of DOAS system, or dedicated outdoor air system. And AHRI has defined it as shown on your screen there. And the key points are that DOAS units are really designed to dehumidify 100% outside air down to a low dew point. And in addition, they also control the reheat, so that you're controlling the supply dry bulb temperature. So those two in tandem are really the key points of a DOAS system. You're treating a ventilation air, usually 100% outside air, can be a little bit less than that. The advantage of a DOAS is that instead of dehumidifying and reheating all of the supply airflow, which for a standard rooftop would include a mixture of outside air and recirc air, you're really only dehumidifying the outside air. So this allows you to have better dew point control, and it's much more energy efficient. So in addition to that, you're bringing in outside air. Typically, you want to be able to measure that and prove that you're meeting ASHRAE 62.1 ventilation rates. And having a DOAS unit allows you to do that much more easily than if you're bringing in outside air at multiple different locations. So moving on, I'd like to talk about some challenges and considerations when designing a DOAS system, just to explain some of the differences in considerations that we have when we're comparing that to, say, a packaged rooftop system. So this psychrometric slide shows multiple state points, and we'll go through those. And the question that typically gets asked when you're laying out a piece of equipment is, what are my design conditions? What should I design the unit based on? And, oh, sorry about that. Jump back to the right slide here. There we go. So we've got state point A, which is our typical cooling design day in Toronto, 8872. Those are in Fahrenheit, dry bulb, wet bulb. And that's a pretty typical condition used for package refrigeration, rooftop units. But what we see when we're just laying out DOAS units is we really want to be using the dehumidification design day conditions, which in Toronto is more typically about 80 degrees, 74 degrees, dry bulb, wet bulb. And with the DOAS unit, you can see there's state point 1 on the psych chart. That's our target. That's what we're trying to dehumidify down to. And if you take that delta in enthalpy between 1 and A versus 1 and B, you'll see that that delta is a lot bigger from state point 1 to B. So that means if you're only designing with your state point A as your design, you're gonna have an undersized system on your dehumidification design day. So that's why it's really important to use the right design day to make sure that the unit can handle that extra moisture load from the outside air. So now I'd like to talk about a part load condition. And if you think about operating during the year, your design day doesn't happen very often. So most of the year you're going to be what we call off peak. And this is, maybe cooler or less humidity, but some variation of that. In this example, we're looking at a 65-degree day, summer morning. So your dry bulb temperature is not that high, but your humidity is relatively high. So what do you do in a scenario like that? Well, you're going to have a DX coil set point that you have to get down to. And to do that, you're going to need some sort of modulation. If you run your compressors at full capacity, they're going to overshoot and overcool, and you're going to end up turning compressors on and off, and your supply temperature is going to fluctuate wildly. And that's not what we want. We want a nice, even supply temperature. We want to be able to modulate. The other consideration is you're going to want to reheat to some set point. You don't just want to supply cold, damp air into the space. You want to be able to reheat so you get that air back up to roughly room neutral. And to do that, we use hot gas reheat. Now, in some cases, you might not be dehumidifying enough from a capacity standpoint in order to get that much reheat. So in critical applications, maybe it's a lab environment where that temperature needs to be absolutely dialed in. you might need to consider having a secondary heat source. And that heat source might already be there for winter heat mode, but it's really important to look at all points of operation where you need to dehumidify down to and what your reheat set point is. So again, there's two state points. There's a dry bulb and there's a dew point, and both of those really need to be controlled too. And a DOAS unit allows you to do that. So we talked about the different modes, but I'm showing them explicitly on this slide here. There's really three distinct modes of operation for a DOAS unit. You have heating mode, cooling mode, and dehumidification, and those are roughly the areas on the psych chart where you'll run into those modes of operation. Now, these modes are fluid, and actually a unit could be operating in those different modes all throughout the range of one day. Imagine fluctuations in temperature and humidity. It's not a very stagnant point. Those can change wildly. So a typical cooling set point would be 72 degrees Fahrenheit. Anything above that, you'd be in cooling mode. Anything below that, you'd be in heating mode. And then a dehumidification set point is right around 55 degrees dew point. And again, those are all adjustable depending on the application. And those temperatures could be outside temperatures, they could be space temperatures that you're measuring, or it could be a combination. So all those factors can be adjusted or tweaked depending on what the application calls for. And to add complexity, the amount of air changes per hour you're doing could affect, the unit operation. You might need more or less capacity at a given time, and also internal loads, of course, affecting what the sensors are reading and what the unit is being called to do. So it's a very dynamic space, very dynamic conditions that are happening. And the DOAS unit is sized to handle those. So in addition to having separate modes of operation, dehumidification, cooling, and heating, so DOAS units can handle those different modes, there are some other key differences between DOAS units and standard package rooftop units. If you look at the coils, typically they're going to be sized to be much larger surface areas and sufficient depth for handling dehumidification, because again, we're dealing with 100% outside air. We need that extra coil surface area and depth. Heating, it's going to have more heating capacity. Again, with the more outside air, you need to be able to have more heating capacity. Control sequences to handle those different modes of operation, of course. Modulating components, and not only modulating components like compressors and heaters, but they need to be able to operate over a wide range of entering conditions, which is really why we have modulation in the first place. And then the cabinet construction is going to have a thermally broken casing. We want to have that unit be very well insulated, have a high R value, want it to be of sound construction so that it'll last and handle those wide range of conditions. And finally, what you'll see on a lot of DOAS units is some form of energy recovery. And if you're bringing in high amounts of outside air, chances are you're exhausting air at some point. And if you can bring that exhaust air through the unit, why not recover some of that energy to make your system more energy efficient? You could actually reduce the amount of heating or cooling load that your unit does just based on the amount of energy that you're able to recover. So these are all some key differences and things to think about when you're designing a DOAS unit. So I'd just like to wrap up this DOAS section by highlighting some key takeaways of the things that we just talked about. So again, it's important to use that dehumidification design day condition for a DOAS unit especially. Spaces that require appropriate temperature and humidity levels, especially the ones that are critical applications, you don't want to be having spaces that are floating temperature, humidity wise, that can lead to variations in the space. You want to be able to control that dry bulb and humidity very tightly. If you start throwing in high ventilation rates, this can make it more challenging. And also the tolerance levels accepted by these spaces can vary greatly depending on the application. So again, we're dealing with 100% outside air, so the range of temperatures and humidities entering the unit can fluctuate wildly, so modulation is critical. We'll talk about modulation in the subsequent slides. And then when you think of DOAS, be thinking about the different modes of operation, specifically the difference between cooling mode and dehumidification. So a DOAS unit's designed to handle all of those modes, and it's critical to think of those when laying out the unit. So now that we've covered these key DOAS design takeaways, Nathan's going to talk more about Valent's product offering.
Thank you, Brian. So just wanted to give a brief overview of how Valent can address these DOAS requirements. The Valent units come in 4 separate cabinet sizes, if you will, that are all configurable in the airflow ranges from 500 to 18,000 CFM. Cooling ranges from 4 to 70 tons with options of packaged or split DX, water source heat pump, air source heat pump, and chilled water for the cooling side of things. On the heating side, we have anywhere from 100 to 1200 MBH of heating up to 100 degree temperature rise. And then we have all matters of different heating sources, whether that be gas, electric, hot water, steam. And then there is another solution called the Temperator, which is a hybrid of gas and electric. This is a solution that was initially, I believe, I felt like it was an excellent fit for labs and areas where you needed very tight control of temperature in spaces. We are starting to also see some interest in the hybrid gas and electric units for those customers looking to reduce greenhouse gases, but not wanting to overtax their electrical on their building. So the electric on those temperators is actually sized to match the electrical capacity of the cooling requirement on the unit as well. So it doesn't affect your overall electrical incoming load. All the units are either capable of 100% outside air or they also can have recirc and modulating recirc dampers on them. So we can meet a very wide range of applications with a single box. And they also come, as Brian had mentioned, with or without energy recovery to create a more efficient solution. Now, speaking about energy recovery, the ERV options available in the standard offering for Valent include a polymer segmented wheel, which is a pretty typical wheel in the marketplace. We do have options of putting a bypass on that wheel, as well as providing an aluminum wheel rather than a polymer wheel. They also do sensible plates, which is an aluminum plate for just sensible heat recovery. That sensible plate is actually built within the Valent plant and is vertically integrated within their building. So it's a great solution for especially areas where obviously you want sensible only recovery, but also areas that are a little bit dirty, maybe plants that you didn't think that were great fits for energy recovery. It's a good solution for that. And then thirdly is the enthalpic core, which is a polymer-based enthalpy core, static core that does both sensible and latent recovery. Where we're seeing a lot of that interest in that is twofold. One, obviously with COVID-19, people concerned of any exhaust air transmission or cross-contamination from the exhaust air stream to the supply air stream. But the other area is on the maintenance side of buildings where a facility may or may not have a on-staff facilities manager that can maintain the wheels or wants to maintain the wheels. This core is a static device, so it really reduces the requirement for maintenance. The other thing that Valent has does very well is they have an integrated controls platform in each of their units. In that they use a standard Corel microprocessor. The standard features of that are a internal time clock, They have a number of temperature control sequences, as Brian was mentioning in DOAS. Really important to have the capability to be flexible in how you manage temperature in the space or discharge air temperature, and be able to see outdoor air conditions and react accordingly. The other standard feature that I believe is really powerful and valuable to the owner is if you connect the microprocessor to the building's network with a simple Cat5 cable, by entering in an IP address, you can get a full, almost BAS in a box sort of solution. At the bottom there, you can see a picture of a typical, I guess, graphic that would come up from connecting your unit to a to the building network. Saves a lot of time in troubleshooting and also setting up your systems. There are also optional features for that, being communication protocols, all the standard protocols with BACnet, NSTP, IP, and LAN talk. And there are some secondary sequences available to help with demand-based ventilation control, CO2 control, and variable air volume. So next I want to kind of talk about where I want to really dig into, because I think on the heating side of things, it's pretty straightforward: gas heat, gas heat, electric heat. And so what I wanted to really dig into here, and maybe get Brian to help us a bit more with getting into the details, is specifically refrigeration. What Valent really does, and really does well in their refrigeration cycles, is digital scrolls. They also have inverter scrolls, hot gas reheat, and some active head pressure controls, which we'll discuss a little further. What they don't do within the Valent offering is hot gas bypass for capacity control, nor do they do evaporator coil bypass for dehumidification control. And we can talk about those things a little more if people have questions about why, but Brian's going to really dig into what they do well. So Brian, from here, I'll let you take it away.
Excellent. So Nathan touched on hot gas reheat, and I alluded to it in my previous slides, but I think now is a good time for us to dive right back in and talk about what that is exactly. So hot gas reheat is essentially a way to take the cold saturated air that comes off the DX coil and reheat it back up to a more comfortable room neutral temperature. So in this psychrometric chart, we're showing we dehumidify down to 50 degrees, for example, and then we're reheating back to 65. So essentially, we're taking recycled energy from the compressor. So normally hot gas that would go to the condenser coil and be exhausted as waste heat. We're going to reclaim some of that heat and use it to reheat our airstream. So it's an efficient process, and in some cases, in a lot of cases actually, when you're in dehumidification mode, it doesn't require any supplemental heat to get you back to your dry bulb set point. Now, I mentioned earlier that let's say you have a lab critical application, maybe you're at part load conditions and you don't have enough capacity for the hot gas reheat because your compressors aren't running as much, then you might need to do some extra reheat with, say, an electric heater or hot water coil or something like that. But when we're in dehumidification mode, typically the hot gas reheat coil is sufficient to heat that air back up to room neutral. So in addition to having hot gas reheat, it's also advantageous to have a modulating valve for that reheat. So the DX coil, like I said, we're cooling down to a certain dew point temperature. And then we want to be able to control how much reheat we have. And we do that with a modulating valve. So again, we're all about tight control. And one of the things that helps us control that very tightly is, it may not seem significant, but it really is. It's a separation between the DX coil and the hot gas reheat coil. And it's typically about 6 inches in our models. And you'll see that picture shows that 6-inch gap. What some competitors will do is put those coils mounted right next to each other to save length. So they're saving 6 inches of length. The advantage of doing it Valent's way is you now have space to put a temperature sensor between those two coils, and that's what's measuring your dew point temperature off the DX coil. So that's how we tightly control the dew point temperature, and then we have another temperature sensor downstream of the hot gas reheat coil, which we're using to measure the dry bulb temperature. So two measurements, two separate state points that we're modulating to. So it helps with control. The space also helps with maintenance, so you can get in between the coils and wash them off from time to time as needed. And the last advantage is you'll see there's a drain pan down at the bottom of the DX coil, and that gap allows the condensate to drain off the coil and out of the unit. If those two coils are mounted flush together, like some of our competitors do, then it's a lot harder for that condensate to drain off, and some of it can get evaporated back into the airstream because it hits the hot gas reheat coil, and that's really not what you want to have happen when your goal is to dehumidify. So, you know, these are some of the design considerations that Valent looks at, and we're very intentional about designing our equipment to give you optimal design control when you're trying to control to a dry bulb temperature and a dew point temperature. So, like I said, modulating reheat is very important for controlling the leaving dry bulb temperature, but modulating the evaporator capacity is also important. And I'll talk about some methods to do that here. The first method I'll bring up is hot gas bypass, and this has been used in the past. It's an older technology, and it works to modulate the capacity of the evaporator, but it's really not an ideal solution. As you'll see in that schematic, the hot gas after it leaves the compressor is a part of it is routed through back to the evaporator. So essentially, with that bypass, you're introducing a false load onto the evaporator, and you're artificially reducing the efficiency of that evaporator to modulate its capacity. So it works to modulate, but it's really not efficient at all. And you know, the modulation that we're seeing now is almost exclusively done by modulating compressors, and in fact, that's all that Valent offers. And we just find it to be a much better solution. So we'll talk about compressors now. And as Nathan said, Valent offers a digital scroll as our standard compressor. And a digital scroll does a much better job in terms of efficiency for modulating the capacity. And you'll see that that little video on the right is showing a cutaway view of a digital scroll compressor in action. So you'll see the bottom scroll is rotating, and the refrigerant enters the scroll, and with that rotating motion, it's compressed until it reaches the very center, and then it's discharged. And then that cycle repeats continuously as it operates. The blue section of the top scroll, you'll see it just moves up and down once in a while, and that's showing the unloading of the compressor. And that's how a digital scroll modulates its capacity. So every once in a while, depending on the signals it receives, it'll unload, and it will reduce its capacity a little bit, and so that's how it modulates. An inverter scroll modulates a little bit differently. Instead of unloading, like that video is showing, there's no unloading, and instead it modulates the frequency of that scrolling motion. So if this were an inverter scroll compressor, it would show that green scroll changing speeds to modulate. Here's a side-by-side comparison of a digital scroll and an inverter scroll and the pros and cons. So like I said, the digital scroll has a continuous rotor speed, and an inverter scroll has a variable rotor speed. You get a little bit better turn down with a digital scroll compressor, down to 10% versus only down to 30% with an inverter scroll, but that's still pretty good. And again, modulation is achieved by that unloading, so the scrolls separate by about 1 millimeter. The inverter scroll, again, the modulation is achieved by adjusting that scrolling frequency. And Compared to a standard scroll, you're going to get about a 30% energy savings with a digital and over 50% energy savings with an inverter scroll. The digital scroll comes in all voltages, and currently the inverter scroll is only available at 208 and 460 volt. So aside from being more efficient, the inverter scroll is actually a lot quieter when it's operating, and it's noticeably quieter. Digital scroll, especially when it's unloading, tends to be loud and noisy, and that's people, if it's a sound sensitive application, digital scroll is probably not the right solution. You're probably going to be wanting to go with an inverter scroll. So this graph here shows a comparative analysis of a digital scroll and an inverter scroll, with the blue is the inverter and orange is the digital scroll. And you'll notice that at anything less than 100% or full capacity, the inverter scroll is much more efficient than a digital scroll. So the digital is a little bit more efficient at full load, but think about how often you're going to be in that full capacity mode. Probably not too often throughout the year. You're mostly going to be in that part load condition. So you're going to reap those benefits with an inverter scroll compressor, just by all that efficiency gain with the system. We talked about compressor efficiency options, but another major way to improve the efficiency of a refrigeration system is with the condenser fan design and operation. Valent uses an owlet blade condenser fan, and there's a picture of it, and you can see it has serrated blades. It looks a little bit strange if you've never seen one before, but those serrated blades are really to help with efficiency of the fan and also for sound. So a standard paddle condenser fan, you'll see on that chart there is right around 90 decibels, somewhere between a hairdryer and a lawnmower, quite loud. The condenser fan that Valent uses is about 8 to 12 decibels quieter, which is pretty significant. So we provide lower sound fans, and then operationally we also offer more ideal control of those fans. So I'll talk about these options in the subsequent slides here. But just to spoil it, we have one EC fan modulating, so that's an option. Or you could have all of the condenser fans modulate together, and we'll talk about the advantages of those. The baseline that we're going to compare to is what we just call standard head pressure control. And that's where your condenser fans are turned on or off based on pressure switches. So the benefits is pretty simple and not very expensive. The drawbacks is you lose reheat capacity at part load because more of your hot gas is being sent to the condenser because the fans are at full capacity. And it's also very loud. So if you can't modulate your fans down, your fans are at full speed, you're going to have the highest sound. The next step up, which we call head pressure control 1.0, is where your lead fan or just one fan will modulate with an EC motor, and then any additional condenser fans will be on or off. The benefit is you have better head pressure control. You're able to modulate one of those fans up and down. So you're going to have quieter sound at part load because you're able to modulate one fan. However, if you're at a high enough capacity where you need to turn on a second fan, now your sound jumps up because one of your fans is at full speed. So this is better, but not quite as good as our version 2.0. So this option is where you have an EC motor on all condenser fans, and they modulate up and down together. So you get better part load sound performance. It's very, very quiet at part load, and increased condenser efficiency. So if all of your fans are modulating up and down together, you're always going to have even airflow across the whole condenser coil. And you're also not going to have backdraft through fans that are off. So this is the most efficient and quietest option, but it's also the most expensive by, you know, a marginal amount. So there are pros and cons, but for performance and sound, this is definitely the best option. So this last slide that I'm going to talk about here highlights an example of some of these different options and putting some horsepower numbers to what I just talked about. So that first row shows a condensing section at full load, and in this case we have 4 fans. They're all 1 horsepower. So if they're all running, you're using 4 horsepower. Pretty straightforward. Now let's consider a case where those 4 fans are seeing a 50% condenser load. So now the controls say, hey, we need to turn off 2 fans. We only have 50% load, so we need half the airflow. Well, 2 fans shut off and 2 fans run. So in this mode, you're using 2 horsepower. And think about the condenser coil. You're not going to pull airflow evenly across that coil. Maybe one half's getting more and the other half's getting less. You're also short cycling air through those fans that are off, so not quite as efficient. In that third row, this is assuming still a 50% condenser load, but now let's pretend our fans all have that ECM setup. So we have EC motors, we're modulating those fans down, and we're able to still operate that same airflow, but at only using a half horsepower. So significant energy savings, and we're getting even airflow across that condenser coil. We're getting excellent heat transfer, very efficient. So having these higher efficiencies allow units to comply with relevant codes. And now Nathan's going to talk about these codes and relevant testing standards.
Thank you, Brian. So I thought it was pretty relevant to just discuss efficiency and codes when it comes to refrigeration in Ontario. There's a lot of misconceptions being spread out, so I wanted to kind of talk through what the codes are and how Valent, I guess, meets those codes. The NRCan obviously is Natural Resources Canada. They're the body that would set federal energy efficiency regulations, but that's only in the absence of provincial direction. There are some of the provinces within Ontario that, within Canada, that do not have a provincial standard. But in Ontario, we have the Ontario Electricity Act. The statute is the Ontario Electricity Act of 1998. That actually was amended just recently, about a year ago, July 1st. And within that Ontario Electricity Act, they refer to Ontario Regulation 509/18, which is the energy and water efficiency for appliances and products. That has a number of different items in there they talk about, but under Schedule 4 within that regulation, there is air conditioning and related equipment. What I've done here is they talk about the different capacity outputs for refrigeration. I have taken just a bit of a focus here on what they're referring to as large air conditioners, which is the majority of the Valent product offering. They do have some that would be considered small, a 4 and a 5 ton, but everything outside of that is considered a large air conditioner, which is from 65 MBH to 760 MBH. So I've taken a little snip from the regulation, just kind of outlining what testing standards they reference. So as you can see in that little snip, it talks about CAN CSA C746, which I'm sure a number of you have heard of. And they also talk about DOE Code of Federal Regulations Part 431. So those are the 2 codes or 2 testing standards that that the Ontario Electricity Act references and are acceptable in Ontario. So if I kind of move on and talk a little bit more about these efficiency standards, it's actually also quite interesting that if you look through Ontario Regulation 509-18, and then you look at DOE Standard 43196 and C74617, they are all consistent with each other in that they reference ASHRAE Standard 90.1 2016 efficiency requirements. Now, this table I'm showing here is not the full table. I've just kind of pulled out the cooling capacities that I'm focusing on in this presentation. That table is much larger and has a lot more information on it, but I've kind of pulled out what's important to today. So I guess in summary of the testing standard, the reference testing standards for Ontario for large air conditioners from 65 to 760 MBH are C746-17 and DOE Part 43196. They differ a bit in that standard C746 actually goes into quite detail on the test procedures needed for calculating the efficiency. So it goes right into what temperatures and what position to set your return air damper at and outside air conditions, and it goes right into the details of it. DOE is a little bit different in that they actually reference a table that tells you what AHRI standard that you are to reference depending on what style of product that you're testing. So one thing I do want you to notice for both of these standards is that both of them talk about vertical air conditioners and heat pumps. There's actually no reference here. They don't talk about 100% outside air equipment or DOAS equipment. Just something to keep in mind as we go to the next slide. So Valent has kind of gone through the DOE list, and they've created a nice little matrix for us to reference as far as how they test their units and get performance for their equipment and are able to conform to the DOE requirements. If you look here, as you go through the start point there, a 100% outdoor air unit or DOS unit is actually to be tested at AHRI standard 920. The interesting thing about AHRI standard 920 is it's not 100% complete yet. And so testing to that is difficult. What's kind of been widely accepted for DOAS units as far as their performance is for them to adopt the performance ratings at a standard operating conditions with return air. So if you kind of move through this matrix, you can see that a cooling capacity for units that are up to 65 MBH are tested to standard 210-AHRI standard 210-240, and the cooling capacity is greater than 65 MBH are tested to AHRI standard 340-360. So I just want to kind of point all that out to you. So what does Valent have from a compliance standpoint? Valent is compliant to DOE, which would be acceptable in Ontario, to AHRI standard 210 for air-cooled under 5 tons. DOE compliance to AHRI 340 for anything from 5 to 63 tons, and ISO 13256, which is a reference standard in the DOE for water source heat pumps, less than 11 tons. What you can do if you're interested is all these the Valent units are shown in the DOE compliance certification database. If you want a link for that, I can provide it. I was going to kind of put it on this slide, but it's really long, the link. So I'm happy to send it to anybody if they wish to see it and look for the Valent equipment. But I told you that. What do we do with 100% outside air? So I told you they adopt AHRI standard 210-240, and just I wanted to also show you that we went as far as with a number of years ago, we went as far as to go to Intertek, who's one of the major testers of equipment, to discover how we would test a makeup air unit or DOAS unit to AHRI to the CAN CSA C746. Effectively, the engineering team lead for Intertek came back to us and identified that a 100% outside air unit is considered DOAS and is not covered under AHRI standard 340-360. And he also confirmed that the labs were not capable of testing DOAS units to what is the current standard AHRI 920. So right now we are in a position where we need to use what the testing and the standards and the efficiencies that are given under the other AHRI standards and codes that are in place for units with recirc air on them. So just an interesting comment in where we're at as far as testing and standards today with DOAS equipment. So what are some of the key webinar takeaways? We're getting near the end here. DOAS presents unique loads. Brian went through that and talked about humidity control, heating and cooling, and wide varying loads, and having the importance of having a product that can address those items well. Valent has a robust and feature-rich air handling solution. Can provide effective temperature and humidity control. Is very configurable to meet a lot of demands. And is also, and the last point is that CSA C746 and DOE 43196 are both applicable energy standards in Ontario. So it's all fine and well to be able to meet all that, but I do want to show you how we went down to Valent when we first started with them, and we had to test these units ourselves. So this is Mike Pillock from our office testing a Valent unit. So it didn't break, and it sounds like a fridge. It's a high quality product. We're really excited to bring it to you and also excited to talk to you in this webinar. So just finishing up, just wanted to see if anybody had any questions, and we'll go from there. Hey, Cam, do you think that you could ask any questions if there are any for us?
Sure, we have one here. It's is the DOAS unit designed by the mechanical engineer of record, or is it the reality that the unit is designed by the supplier?
Oh, that's an interesting question. I would say it's probably a little bit of both. The design engineer of record specifies what conditions to design to, so you know what sort of performance he wants, or he or she wants. But then at getting down to the granular level, you know, the manufacturer is the one that decides, okay, how do we provide components to do the desired performance? So, you know, we'll choose the type of compressor in terms of, you know, which brand of compressor we'll use. But, you know, as Nathan pointed out, there's a lot of configurable options. So the design engineer really does have a lot of control over even choosing, you know, inverter scroll or digital scroll. You know, those are options, different head pressure control options. Do you want energy recovery? What type of cooling do you want? Do you want air cooled, water cooled? Do you want hydronic? You know, there's a lot of different options to choose from. And once those decisions are made, that's when the manufacturer then comes in and executes on those. And you know, so it's a little bit of both, certainly.
Yeah, I agree with that. That we really count on the engineer to give us the loads and what they're looking for. We work with the products to fit them into the needs of the engineer. So the engineer is pretty critical in the whole decision making.
Okay, and the next question, can you discuss how DOAS works well or not with VRF in terms of humidity control where ventilation levels are quite low?
So DOAS, in my opinion, works very well with VRF. The DOS solution would allow you to obviously maintain and address any humidity issues going into the space in the summer, without having to put that load onto the VRF system itself. So it not only does it help to improve building comfort, but it also helps to improve the efficiency and operation of the VRF system itself. So that I would say that that's a match made in heaven, really, to operate those two items together.
Okay, and I believe that's it for our questions.
All right. Well, again, everybody, thank you very much for joining us in this webinar in isolation intelligence from Odell. As I mentioned at the beginning, this presentation will be available on our website within probably 24 hours. You can grab the slides as well as the video of the presentation. So thanks again, and I hope everybody has a great day, and we'll hope to talk to you soon. Thank you.